Good morning, one and all. This is Dr. A. Chetan Krishna. Welcome to AGEA Electronics Academy YouTube channel. In this channel, now in this video, we are going to discuss about the derive the Maxwell's equations for static fields. Here in this question, the JNTH may ask the question, derive the Maxwell's equation for the static field. Here, Maxwell's equations for static fields means we have the total four Maxwell's equations are there. In these four Maxwell's equations, we these four Maxwell's equations for the static fields. Now we are going to derive the four Maxwell's equation for the static fields. In the static fields, we have the two static fields are there. One is the electrostatic fields and magnetostatic. Before going to discussion, now what is the static fields? Here, static field is nothing but there is no any time involvement in the field. Means there is no any time involvement in the field. Means there is uh, the time should not take in, the time should be a constant, the time should not affect the field. That field we can call as a static field. Now we are going to discuss or we are going to derive these Maxwell's equations for static. In this one, the first we are going to discuss about the electrostatics. The first we have to going to discuss electrostatics. In this electrostatics, the first Maxwell's equation we are going to discuss by the Gauss law. First Maxwell's equation we are going to discuss by Gauss law. Here Gauss law is a fundamental law. This Gauss law states that here the Gauss law states that Q enclosed by the path is equal to the total flux enclosed by the surface. Means here whatever the total flux enclosed by the surface, that is the equal to charge enclosed by the surface. Charge enclosed by the surface. Here, based upon this one, the total flux we can write by the equation psi is equal to integral d dot ds. This should be a closed surface. Here, the electric flux should be a closed surface. This electric flux induced by the closed surface is equal to charge enclosed by the surface. Here, the total charge enclosed by the path that is equal to, here we may write as a volume integral of rho v dot d. This is the total charge enclosed by the path. Now here in this one, the psi should be the closed integral d dot ds, that is equal to q enclosed by the path is equal to rho v dot d. Now based upon this first equation and this second equation, we may write that one integral d dot ds equal to volume integral of rho v dv. Volume integral of rho v dv. Now we can apply the divergence theorem to this one. We can apply the divergence theorem to this one. The divergence theorem states that closed path integral of any vector, closed surface integral of any vector, that should be a divergence of volume integral. The divergence of the volume integral of that particular vector. Divergence of that vector in a volume integral. By this equation, by this divergence theorem. And divergence theorem is also a very important. The divergence theorem, it states that surface integral should be converted into volume integral by the divergence we can apply for that vector. We can apply that vector, then only the divergence theorem should be applied. Whenever the closed surface integrals, only we can apply the divergence theorem to volume integral, that should be converted to volume integral. Now here, this equation we can write as a integral volume integral of del dot d into rho v dv, that into dv, that is equal to integral volume integral of rho v dv. By the comparing these two, we may write del dot d equal to rho v, del dot d equal to rho v. This is the first Maxwell's equation. The first Maxwell's equations for the first Maxwell's equation for electrostatic field. The first Maxwell's equation for electrostatic field, del dot D equal to rho. Here, this is the first Maxwell's equation. The first Maxwell's equation is states that divergence of a the divergence of a electric flux density, the divergence of a electric flux density is equal to volume charge density. Volume charge density. That divergence of a electric flux density is equal to volume charge density. That is the first Maxwell's equation. The first Maxwell's equation. Now we are going to discuss now the second Maxwell's equation. The second Maxwell's equation. The second Maxwell's equation The second Maxwell's equation we can state that we can write from the electric potential. From the electric potential. That electric potential. The electric potential. Now, electric potential is states that by using this electric potential, we can write that electric potential. We know that the electric potential in a closed surface, electric potential in a closed surface or closed line, that should be equal to zero. Means here closed line electric potential in a closed line or in a closed path, that should be equal to zero. That should be equal to 0. Closed path, that is equal to 0. Based upon that one, we can write the electric potential equation integral E dot dl equal to 0. Integral E dot dl is equal to 0. That is we can write as a VAB minus VBA. Means this should be a closed surface A to B and B to A. A to B and B to A, the potential should be equal to 0. That's why any closed path, the electric potential should be equal to 0. That's why electric potential we can write as a E dot dl is equal to 0. Now for this equation, we can apply the Stokes theorem. We can apply the Stokes theorem. This Stokes theorem states that closed line integral of a vector the closed line integral of a vector that is equal to closed line integral of a vector that is equal to surface integral of a curl of a that vector. Surface integral of a curl of a vector means Stokes theorem states that any vector in a closed line that is equal to surface integral of curl of a vector. This becomes as a Stokes theorem. According to the Stokes theorem, this equation we can write as a integral surface integral of del cross E bar dot ds that is equal to 0. That is equal to 0. From this equation, we can write as a del cross E bar, del cross E or del cross E bar that is equal to 0. This is the second Maxwell's equation for electrostatic field. Electrostatic field. Here this is the del cross E is equal to 0 is the second Maxwell's equation. Second Maxwell's equation for the electrostatic field. Now this is the first Maxwell's equation. First Maxwell's equation is states that del dot D equal to rho v. The second Maxwell's equation we can state that the del cross E bar is equal to 0. Here we can apply the divergence theorem. Here we can apply the Stokes theorem. Here we can apply the divergence theorem. Here we can apply the Stokes theorem. Here the divergence theorem applied, then del dot D equal to rho v it will come, and whenever the Stokes theorem it will apply, that should be becomes as a curl. These all are the electrostatic fields. Electrostatic field Maxwell's equation. Now we can write as a the same methods we can here we can discuss the magnetostatics. Magnetostatic fields. Here in these magnetostatic fields, also two Maxwell's equations are there. In the magnetostatic field, also two Maxwell's equations are there. These Maxwell's equations we can derive the first one. We can derive the first one we can derive from the Ampere's law. The first one we can derive from the Ampere's law. Here Ampere's law is states that the Ampere's law is states that closed line integral of closed line integral of closed line integral of magnetic field intensity closed line integral of magnetic field intensity that is equal to I enclosed by the path. That is equal to I enclosed by the path. Here this we can write as a Ampere's law. Ampere's law states that closed line integral of magnetic field intensity that is equal to I enclosed by the path. I enclosed by the path. From this equation, this side whatever the integral h dot dl, we can apply the Stokes theorem. We can apply the Stokes theorem. Then already I told that Stokes theorem is states that integral a dot dl that is equal to surface integral. It becomes as a curl of a surface integral of a vector. Based upon that one, we can write as a equation integral surface integral del cross h bar del cross h dot ds del cross h dot ds. Now here this is equal to, we can write as a h dot dl. We can apply the Stokes theorem. Now here this I enclosed by the path we can write as a I is equal to equation is there. The I is equal to in terms of current density we can write as a J dot ds. That's why we can write as a current density J dot ds, that is equal to I enclosed by the path. I enclosed by the path. Now comparing these equations, we can write as a del cross H is equal to J. Del cross H equal to J. Del cross H is equal to J. This is the first Maxwell's equation for first Maxwell's equation for first Maxwell's equation for magnetostatic fields. The first Maxwell's equation for magnetostatic field, that is derived from the Ampere's law. Ampere's law states that closed line integral of magnetic field intensity, that is equal to I enclosed by the path. We can apply the Stokes theorem to H dot dl. We will get as a del cross H dot ds. Then we can apply the I enclosed by the path is equal to I is equal to integral J dot ds. Then we can write as a del cross H is equal to J. This is the first Maxwell's equation for magnetostatic field. Now the second one. Now the second one we may derive from the second one we may derive from the magnetic flux density. Here total magnetic flux psi is equal to wherever the same as a B dot ds. B dot ds. Here B is the magnetic flux density, whereas a D is a electric flux density. Here magnetic flux density is a D. Here whenever the in this one whenever this B dot ds is there, whenever the magnetic flux total flux psi is equal to integral B dot ds, the B is a magnetic flux density. This magnetic flux density we can write as a B equal to mu naught. B is equal to mu naught into H linear. Now, whenever we can take in as any closed surface, this magnetic total magnetic flux, any closed surface, this magnetic flux B dot ds, that is equal to 0. Why this B dot ds is equal to 0 means identical uh, magnetic field does not exist. Identical magnetic flux does not exist. Means wherever we can take it as any magnet, the north and south pole should also there. If we make, if one magnet should be a cut it, then that magnet also a north and south. Here, north and south pole we cannot divide, or we cannot divide the north and south poles from the magnet. That's why any closed surface, the total magnetic flux is equal to 0. Any closed surface, magnetic flux equal to 0. Now we can apply the divergence theorem to this equation. We may get the divergence theorem already states that any closed surface integral of any vector, that is equal to divergence of a volume integral of a divergence of that vector. Then this equation we can write as a volume integral of del dot b into dv, that is equal to 0. From this equation, from this equation we can write from this equation we can write del dot B equal to 0. Del dot B equal to 0. This is the second Maxwell's equation for magnetostatic fields. Second Maxwell's equation for magnetostatic fields. Now we have derived the two Maxwell's equation for electrostatic fields, two Maxwell's equation for the magnetostatic fields. Now here we can write the summary. Of these four Maxwell's equations. Uh, we may write as a differential form, differential form, integral form, and remarks. The four Maxwell's equation. The first Maxwell's equation we can write from the Gauss law. From the Gauss law, we can write as a differential form. Differential form del dot D equal to rho v. From the Gauss law, we can write as a del dot D equal to rho v. Whenever we can apply the divergence theorem, we can write as a del dot D equal to rho v. Whenever we can write as an integral form, closed surface integral of d dot ds, closed surface integral of d dot ds is equal to q enclosed by the form. This q we can write as a integral rho v d, integral rho v dv. Here this first Maxwell's equation we can derive from the Gauss law. Derive from the Gauss law. The second Maxwell's equation, the differential form is del cross E equal to 0. Del cross E equal to 0. Then we can write as a integral E dot dl is equal to 0. Where we can derive these equations means here we can electric potential. From the electric potential, we can derive the del cross E is equal to 0 and integral E dot dl is equal to 0. From the electric potential, closed path of electric field intensity, that is equal to 0. Then we can apply the Stokes theorem. We can get del cross E is equal to 0. Next, the third one is del cross H equal to J. Del cross H is equal to J. This we can write as a integral H dot dl equal to I enclosed by the path. This we can get from the Ampere's law. Ampere's law. From the Ampere's law, we can derive this equation integral H dot dl is equal to I enclosed by the path. Ampere's law states that any closed line integral of magnetic field intensity that is equal to I enclosed by the path. Now next fourth one is del dot B equal to 0. You have one doubt. The differential form we can write del dot D. Del means here del is nothing but differential vector component that we are already know dou by dou x plus dou by dou y plus dou by dou z. Now this integral form should be the integral B dot ds equal to 0. Why? The identical magnetic field does not exist. This we can write as a from the magnetic flux density. Magnetic flux density. These all are the Maxwell's equations from the static fields. Maxwell's equation from the static fields. Now, the next video we will discuss about the Maxwell's equations for time varying fields. Maxwell's equation for time varying fields. Up to now, these Maxwell's equations for the static fields is very important, very important for you people, and you may get the question in the uh, exam also. Exam also. Okay, right? Now we can end up the session. Next video we will write as a we will discuss about the magnet electric Maxwell's equations for time varying field. Right? Thank you.